Hello, I'm Jinzhu Wang. In last video, we have walked through how Luto solver can translate those requirements into mathematical expressions. In this video, we will have another high-level and deeper walkthrough of how exactly Luto works with input data. First, we need to understand some notations of Luto on the input data and how it organizes different variable space. Suppose this is all the pixels of Australia. Now, for each pixel, it have two states, either dry land or irrigated land. For any of these water supplies, it can further be segregated into three additional status. Each pixel can be either an agricultural pixel or non-agricultural land pixel, or the pixel can have an agricultural management status. In Luto's notation, we use R to represent each pixel, the M to represent the water supply, dry land or irrigated land, and we use the little j to represent the land use status. In practice, we use K to represent non-agricultural land, and we use P to represent the products. But for simplicity, here we just notice that we use a little j to represent the third dimension. In Luto, we have nearly 7 million pixels, so the length of the R is nearly 7 million. And the water supply is 2, and the land use types are 28. Let's observe Luto from the highest level. For example, in the year 2010, we have 7 million pixels. Each pixel has two potential water supply, and under each water supply, it can have another potentially 28 land use state. So we can use this many number to represent all possible states of 2010. And with Luto server, we can transform each of the states into the year of 2011. But how exactly a pixel can be transformed to the following year? We will use an example of greenhouse gas to show how this transform happens. Let's go back to the Luto project. We can find the greenhouse gas calculation under Luto directory, the economics and agricultural subdirectory. Here we can find a ghg.python file. We can also find another GHG under non-agricultural subfolder, but those are logically the same. So let's get into this GHG. In line around 200, we can find this function, get GHG matrix, which requires all the input data and a year and an default aggregate argument. Let's observe this line. It will return a GMRG. Please note this MRG. This is the standard notation of how Luto describes the variable space. Let's go back to our slide. We have inspected this getGHG matrices function. What it has tried to do is to transform all input data into a GMRJ. And this GMRJ means that for each pixel under different water supply and additionally giving each potential land use, what is the exact greenhouse gas emission of that pixel? We can easily calculate that the total greenhouse gas emission is 100 million tons. Now, we can ask Groby to reduce 10 million tons on top of all those pixels by reducing or removing some pixels. So Luto received this order, it will start the transformation job, and in the end, it will hand over another MRG format of pixels, and all the pixels will sum up to 90 million tons. Yes, Luto also has to consider a lot of other variables such as water, revenue, and biodiversity. Now, let's have a total view of all those functions. We can observe that there are greenhouse gas, quantity, water requirement, cost, revenue, transition cost, and a biodiversity requirement. All those functions will create an MRG variable space. Another bit of information we need to consider is that all those functions only works with agricultural pixels. For example, for the greenhouse gas, when we scroll down, we can say there's get greenhouse gas transition penalties. And let's scroll down even further, we can see there's get asparagopsis effect greenhouse gas MRGs. Asparagopsis is one of agricultural management. Let's go back to the slides. So for agricultural, it has the 7 decision functions, and it also has these functions for non-agricultural and agricultural management. So all those functions are creating the decision space for Luto Solver to optimize future land use. For simplicity in this slide, we only taking the agricultural land use as examples. After creating this decision space, we need to provide another table of constraints for the server. For example, we know that greenhouse gas need to be reduced million tons. Luto Solver will get into the decision space. It will remove some of the live pixels and planting trees on top of those livestock grassland. For water requirement, Solver will go and find the most water consumption pixels and cut off those pixels and transform those pixels, for example, from apple trees to winter cereal. All in all, those constraints will provide the limit for the server to manipulate with all those pixels. But here exists a problem. If we want to reduce the greenhouse gas emissions, we can either remove the pixels of livestock or we can plant more trees. That means for this nearly 7 million pixels, Luto Solver will have infinite solutions to achieve the greenhouse gas reduction target. This can boil down to one question: what is the best solution for all those solution spaces? To get the best solution, we have some modifications. We have removed all those cost and revenue to another set of decision space. And for Groby, except for constraints, we can also set objectives. So we summed up all the revenues and all the cost, and we told Luto Solver that we want to maximize the revenue as well as minimize the cost. So even though here we can get infinite solutions for greenhouse gas, water, etc., we ask Luto to get the one that spends the less money and get more revenue. With these two limitations, we can finally get a solution that is the best. Go back to the Luto code. Here in Luto solvers, we can find this set objective function, which is trying to do that exactly what we just talked about. It has two modes. If the objective is to maximum revenue, we will use this agricultural revenue. Please note this MRG. It means it is a decision space. We will use all the revenue to minus the cost from agricultural and cost from agricultural transition and cost from non-agricultural to agricultural transition. By subtracting the cost from revenue, we want this value to as big as possible. So that's max revenue. Similar way, if we set the mode to mean cost, we will only add up agricultural cost, agricultural transition cost, and the non-agricultural to agricultural transition cost. And we want cost as minimized as possible. That is how Luto mathematically to achieve the optimization function. Now let's have another walkthrough of those solver.py. Everything should come clear to us. Let's get into this Luto Solver. First, in this initializing process, Luto Solver is reading all the input data and the demand data, and it is creating a Groby model. In the next block, it is creating an empty space to hold constraints. Those constraints are regulations on how many greenhouse gas should be reduced, how many water should be used, in the next year. In this block, it is initializing the variables. Those variables are the best solutions the Luto can find, but right now they are all empty values. Next, in this setup variable wrapper function, we can see Luto solver is reading all data into the empty space it just created. Here, in the setup constraint function, it is adding the constraints to the empty space. For example, it is adding cell usage constraints, adding the greenhouse gas emission limit, biodiversity limit, etc. Following up is this set objective function. We just talked about this. It is essentially trying to find the best solutions. Because Luto can find infinite solutions for greenhouse gas, water, and so on, so we will use this max revenue or minimize cost to force Luto to find the best solution. Following the objective function is this update variable function. This is an engineering measure to make sure Luto solver uses as less memory as possible. We know that Luto has to deal with 7 million pixels, but from one year to another year, if there's only 1 million pixel has changed, there should be no need to record the rest 6 million pixels. And this function suits a purpose for that. It will only update the variables that has changed from one year to another year. And last is the solve function. This is the function that glued all the function we have talked about into one function and simulate the land use change year by year. This is generally a loop through each variable and a loop through each decision space and get the result. This is for the tutorial today. We have a walkthrough of the high level and the detailed implementation of the solver and the simulation of Luto. In next tutorial, we will talk about report and tools modules.